Simple regression is a great way to compare bivariate data, meaning two data points that are associated with each other. So let's go through and take a look at how to calculate a simple regression equation using some data. Let's suppose we have data on moviegoers and how much they're spending on snacks. We have a sample size of 10 people. We have their age, and we also have how much money is spent. So let's go through first the calculations by hand, and then I'll show you how to do those as well in Excel. To start with the equations, we're going to start by taking our value of x minus our average, which is our x bar. So to do that, we're going to start by summing up our values for our age, which is our x value, and then calculating the average of our ages. Our x minus x bar then will be each individual age minus the average. So I've calculated those here, and we now have all of our values in for x minus x bar. For our equation, we'll also need our y minus our y bar. So to do that, we'll also calculate our sum for our values of y, which is 92.55, and then also our average for our y values. So then our y minus y bar will be each value in our C column minus our average for y. So then we have our values for our y minus y bar. The next step that we'll need is our x minus x bar squared. So this is our values from column D. So we've squared those values. Next, we also want our values for y minus y bar squared, which is squaring the values from column E. So now we have those values. The next step of this is taking our x minus x bar and multiplying it times our y minus y bar. So this is our, in the first case, D4 times E4. And then we have our values. The last piece that we'll need to do this by hand is taking our y values and squaring them, which is from column C. So when we square those values, we now have them. So that gives us the information we need to start creating our regression equation. Our value for n is 10 because we have information on 10 moviegoers. Our degrees of freedom then is B16, our value of n, minus 2. And it's important to note that it's minus 2 because we have two variables here. We have a sample that's related to age and a sample that's related to the money spent. So we're losing two pieces of information. So it's our degrees of freedom is our sample size of n minus 2 for simple regression. Our alpha value, we're going to set at 0.05 for 95%. And now we can calculate our sum of squares for xx. So to calculate our values for the sum of squares for xx, sum of squares of yy, and sum of squares of xy, we're also going to take our sums and our averages from our values from this table. So we're going to use the sum for each of these columns. And now we've got the values that we need. So for our sum of squares for xx, this is our value from F14, which is our x minus x bar squared. And we took the sum of that column. Our sum of squares for yy is going to be calculated by taking I14, which is our sum of our y squared values, minus C14, which is the sum of our y values, squaring that value, and then dividing by B16, which is our value of n. So we end up with a value of 39.6122. Our sum of squares xy is equal to h14, which is our sum from column H, the x minus x bar times y minus y bar. So now we have important pieces of our equation. Our correlation coefficient is going to use those values. So it takes B22, which is the sum of squares of xy, divided by the square root of B20, which is sum of squares xx, multiplied by B21, which is the sum of squares of yy. So we have our correlation coefficient. We can use the correlation function in Excel, which is Correl, C-O-R-R-E-L, and we're going to take our values from X, B4 through B13, and then our values from Y, our second array, which is C4 to C13. And that also gives us the same value, just a much easier way to go through and use a correlation function, whereas we had to do quite a few functions within Excel to get through it manually with Excel. Our R squared value then is going to be our correlation coefficient squared. So we have a value of 0.0851. We can use that information then to determine the percent of variation that we have. So we have 8.51% of variation. So that tells us how well our model predicts based on the relationship between those two variables. And in this case, our R squared value is extremely low, which is showing that there's no relationship between the age of the person and how much money they spend at the movie theater. So the way we would also set this up from a hypothesis standpoint is that we would state the hypothesis. Our null hypothesis would be that P is equal to 0. Our alternative hypothesis is that the P is not equal to 0. In step 2, we would specify the decision rule. We would reject our null hypothesis if our T calculation is greater than our T table. We would calculate that using the T dot inverse dot 2T tail based on our probability. And that comes from B18, which was our value of 0.05, and our degrees of freedom, which was 8. So our value for our T table is 2.30. In step 3, we would calculate the test statistic. So this is our value based off of our data using B25, which is our correlation, multiplied times the square root of B16, which was our sample size of 10, minus 2 to get our degrees of freedom, divided by 1 minus B24, which was our correlation coefficient squared. So that gives us a test statistic of 0.863. Then we're going to make a decision using that based on the T calculation compared to the T table. We're going to reject the null hypothesis if the T calculation is greater than our T table. So I've set up logic here where if B38, which is our T calculation, is greater than B35, which is our T table value, we're going to reject the null hypothesis. Otherwise, we're going to fail to reject the null hypothesis. In this case, we're going to fail to reject the null hypothesis. Our p-value then we can calculate as well to understand the confidence in our results using our t.dis.two-tailed, taking the absolute value of B38, which is our test statistic, and we're going to take the absolute value, so it'll be positive 0.863, and then our degrees of freedom from cell B17, which was 8. And that will tell us that we have a p-value of 0.4133. So in this case, we're going to fail to reject the null hypothesis. Our p-value is quite high, so we don't have a whole lot of confidence within it. However, what we're going to stay here, though, is that there's a very small relationship between the age of the person going to the movie and the amount of money that they spent on snacks.